you bring in last week's one? You need a stapler?
It's okay, where are we going?
Do you have any questions from last week?
Other items besides carbon. First will be lone pairs. Like lone pairs of high energy level than compared to the hybridized orbitals, or what?
No, right? If you were to refer to this part, the summary, this part, it says that for every lone pair you need one hybridized this orbital, correct? And for every sigma bond you need one of these hybridized orbital. So since both are hybridized, both have the same energy level, right? But although we talk about same energy level for this case, right? In other words, if you were to look at the case for nitrogen, it's from group 5, correct? 1, 2, 3, 4, 5. So in order to form ammonia, like NH3 with a lone pair, what you do is that you apply this rule, you realize that you need 4 orbitals because there's 3 sigma bond and 1 lone pair. So these will actually hybridize to give you your 1, 2, 3, 4 sp3 orbitals. But this sp3 orbital is a bit different from your methane, CH4. For this, you have an orbital with 2 electrons, and the others will just have 1. So one of these will form a bond with hydrogen, 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 and this is the lone pair, right? So although we say that they are of equal energy level, you should know that for most reactions, ammonia, right, it is the lone pair that is reacting, not really these bonds, right? Now one reason you can think about it is that these electrons are held between 2 nuclei, while this electron is only held within 1 nuclei, correct? So this attraction is stronger than this, therefore this is more reactive, right? Yep. Next question.
That's good there. It's like means like it dissociates in water more easily from H plus ions, but then for this SP1, wouldn't it be, since it's stronger?
I'm not talking about the CC, but I'm talking about the CH. Yeah, not the CC. So you have this alkyne. After it loses H plus, it become R, C, C minus plus the H plus. Right? Now for the alkene, same thing. Let's say you have these species, you can lose hydrogen to form this plus H plus, because acid base is about breaking something X bond, something H bond, correct? So he's talking about breaking of this bond, not this bond. This bond is easier to break, and this bond is easier to break, and this bond is harder to break, but this species is more stable than this species, precisely because of this negative charge residing in the sp orbital. For this is a sp2 orbital, correct? So we have learned that sp orbital have greater s character, so it's closer to a nucleus. So this charge is more stabilized. While for this charge, it's further away from nucleus because it has less s character, so this is less stabilized, right? So that's why this is more stable, and the equilibrium, right, will be more favored because you know that acid base is the equilibrium process, right? So it's more favored for this than this, which makes this more acidic, right? That's all right. The naming part, not so much of a problem. You just need more practice on naming.
I think I still pretty wrong.
It's okay, right? Remember, it's the electrophile part, right? You stop at the electrophile part. Yes, this part. Okay, so we have talked about nucleophiles. Next, we talk about electrophiles. They are electron-poor species, either positively charged or electron deficient. So I classify them under 4 categories as well. Those that are positively charged. So what can you tell me? What are some examples that you can think of? Nitrate? Which one? What's the formula of the nitrate that you're mentioning?
That's negative.
If you're thinking about NO2+, yes. Right, there's one species. This is known as your nitro, if I'm not wrong, it's nitroso, right? Or is it nitronium? I forgot. But anyways, you have your NO2+. That's definitely belongs to your first category. What else? H+, yes, of course, right? Have you learned arenes yet?
No.
Oh yeah, okay. In fact, as you learn more about organic chemistry, you will encounter more of this kind, right? Another kind is your Br+, right? When you learn arenes, you will realize, you will know how this is formed, right? For now, you just have to know this few. Next are those which have empty orbital or electron deficient species, which we call it Lewis acid. You have learned about Lewis acid and base in acid base, right? Whereby your neutral nucleophiles can be considered as Lewis base. Of course, the others can also be considered as Lewis base, right? So what species can you think of? They have empty orbital. Usually your boron containing species will have an empty orbital, or you can say that they are electron deficient, right? So what boron species can you think of? BF3, yes, of course, yes, that's one. You can have your AlCl3 as well, right? There's also electron deficient. Apart from this, you can also have your carbocation, right? Whereby you have a positive charge on C, or you can say that there's a empty orbital on C, because if you were to look at this carbocation ion, right, the positive charge actually resides on an empty p orbital, right? So this C is actually sp2 hybridized with positive charge in the unhybridized p orbital, right? And next, polarized multiple bond species. These can also act as electrophiles. So for example, you can have your carbonyl compounds, right, with this CO double bond group. These can act as an electrophile because oxygen is electronegative, so you can pull electron clouds away from carbon, which means that oxygen can acquire a partial negative charge, while carbon acquires a partial positive charge. Right, so people usually draw it like this. And apart from CO double bond, you can have CN double bond, right? Remember, CN is linear because these two are sp hybridized. So same thing, these can acquire a partial negative charge. This one is can get a partial positive charge, right? These are what I call polarized multiple bond species. And last one is your polarized sigma bond electrophiles. So instead of having a multiple bond, you can have a single bond, right? C bonded to Cl. Same thing, Cl is quite electronegative, so you can pull electron cloud away from C, so you can get the same effect, right? So you can have this. You can of course replace this with another electronegative element, so for example oxygen, nitrogen, etc., right? So now if you were to compare this with this, right, you will see that there's a few species which can act as both a nucleophile and an electrophile. Which are they? You sure? Which one? This one?
Polarized sigma bonds.
Okay. Because when you have a polarized sigma bond, you should have and if let's say there's a lone pair here, you should have this acting as a nucleophile and this acting as a electrophile, correct? Even without the lone pair, you can still act as a electrophile, for example this case, because the bond is obviously polarized. Apart from this, you have this carbonyl compound which can act both as a polarized multiple bond electrophile or a neutral nucleophile, right? So these are just some of the many species which can act as both an nucleophile and electrophile. So now, why do I ask students to do this exercise? Because later on you're going to see a lot of reaction mechanisms. Have you dealt with them already? Which is the free radical substitution, right? Okay, later on you're going to see a lot of other kinds of reaction mechanisms. So it's very important to identify nucleophilic sites and electrophilic sites. Nucleophilic sites are like electron source, while electrophilic sites are electron sink, what we call. So for example, like this case, a very generic nucleophile and an electrophile, when they undergo organic reactions, we draw the arrow like this to signify that, okay, the electron flow from the electron source, which is the nucleophile, to the electron sink, which is the electrophile, right? This actually help organic chemists to determine what is the final product, right? Now it's very, very important because if let's say you have a molecule like this, right? Never see before, right? If let's say you have a molecule like this and then I ask you to predict what is the product, even without knowing what is the reaction, or even without learning this actual reaction, you can predict the product. Okay, how you do it? Very simple. First, always identify where is the nucleophilic and electrophilic site. So let's look at the nucleophilic site first, right? And then we look for this form. Of course, this one is not present, right? Because it's neutral. Next, second one, neutral nucleophiles with lone pair. Okay, we have a lone pair here. So these can act as a nucleophile. Where else? Next, unpolarized multiple bond. There's no unpolarized multiple bond. This bond is polarized, so we don't count that. Next, polarized sigma bond. Do we have a polarized sigma bond? Yes, we have. Lithium and this, correct? So which one is more electronegative? Lithium or carbon? Carbon, the electronegativity is like that. So this is carbon, which is more electronegative, so we can put a delta minus. In fact, we can put another delta minus here, right, since it's nucleophile. So now we have identified all the nucleophilic sites. And then next we identify the electrophilic site, right? Same thing, we follow these 4 rules and we will realize that there's actually only one electrophilic site, which is here, with a delta plus, right? So since we have identified the nucleophilic sites and electrophilic sites, we can go ahead and predict what's the reaction. Like what I mentioned, nucleophiles will react with electrophiles. Nucleophiles will never react with a nucleophile, right? So now you have 2 nucleophilic sites. One of them will definitely attack the electrophilic site. So which one you think will attack the electrophilic site? Will it be this or this?
The oxygen.
No, it will be this. Correct? Why will it be this? It's really connected to it, right? If it's self-attack, then there's nothing to talk about, right? So in fact, later on you will understand, you will learn about this reaction, right? So don't worry. So for now, just appreciate how this is useful, right? Why this is useful. So now you have a carbon and you have a electrophile here, right? So what you will do is that, remember last lesson I told you that whenever you have this kind of species, right, you can think of it as this carbon with a negative charge, right? It's the same thing. So now I just erase away the other things. So you have this species which will attack the electrophile. Remember this arrow, right? It's always from the nucleophile to the electrophile. The electrophilic site is here, so I draw the arrow to here. So this is in fact the reaction mechanism, right? Once you know the mechanism, you can draw the product with ease. 1, 2, 3, 4. So what you get is a 4-member ring with O minus, right? Of course, in order to draw the complete steps, you have to understand more about reaction mechanism. So for now, I just draw you the product, right? So in fact, this is your product. Okay, it's just a simple ring closing reaction, right? And now the question becomes, does it mean that I can choose any nucleophile here and any electrophile here, then they confirm will react together? No, the answer is no. We still have to see how good the nucleophile is and how good the electrophile is, right? And if let's say I have a poor nucleophile and a poor electrophile, reaction may not occur. Sometimes reaction can occur if let's say you add another species, which is the catalyst, right? Or some solvent which will accelerate the reaction. Otherwise, they will not occur, right? So that's for nucleophile and electrophile. Next, radicals. Radicals have an unpaired electron and is very, very reactive, right? You have learned about the Cl radical, correct? Which is this, right? So let me ask you, for this radical, what is the oxidation state? No, it's 0. Right? Remember, chlorine got 7 electrons. Now just nice it got 7 electrons. It doesn't have any extra, it doesn't have any less. So its oxidation state is 0.
But 7 electrons now, yeah, that means the charge is still negative.
If you are talking about negative, it's this species, right? Chloride, whereby it gained 1 extra electron from somewhere, then you'll be negative.
Oh.
Right?
Right, yeah.
So this chloride radical has an oxidation state of 0, so don't confuse, right? So apart from your Cl radical, what other radicals can you have? Br, of course, right? And other radicals, blah blah blah, right? Later on we'll see how radicals are formed, so for now you can just write these two as the example, right? So next type of organic reactions. For this type of organic reactions, you don't have to know their reaction, right? For example, reaction has a name. You don't have to know their name to classify them. You can classify all of these just based on what's the reagent, what's the product, right? So for example, the first one, addition reaction. Two substances react to give a single product, usually occur in unsaturated molecules. So for example, addition, right? If I want to use the if I want to explain this to a layman, I will just say that okay, it will be A plus B to get C. Only one product, right? And for addition, I can further classify it into two. So first is my electrophilic addition. So whenever you have all these electrophilic addition, electrophilic substitution, electrophilic blah blah blah, right? Usually the non-carbon based reagent is acting as the electrophile. Means if let's say I have a species with carbon, the other species, which I call it the non-carbon based, right, will be acting as the electrophile. For this case, it's quite obvious because we already classified nucleophile and electrophile, right? For this, it can only act as a nucleophile, unpolarized multiple nucleophile. So this will be acting as a obviously an electrophile, right? So after this reaction, in fact, this reaction you already learned in O levels, which is your decolorization of the bromine water, right? Which is this. So this is known as a electrophilic addition because the non-carbon based reagent is acting as an electrophile. So it's called electrophilic addition, right? No matter it's electrophilic addition or nucleophilic addition, you must always fulfill this criteria, right? So this is your EA, electrophilic addition, which you will learn in alkenes. Or have you learned it already? Learn already, okay. This is your electrophilic addition. So if electrophilic addition, no problem. Next will be nucleophilic addition, right? So for nucleophilic addition, make a guess which species is acting as a nucleophile. Same thing, the non-carbon based, right? For this nucleophilic addition, you usually involve, I'm not saying must, involve a carbonyl species plus a nucleophile. So the nucleophile can be water, can be ammonia, can be anything. So I'll rather give you a generic one, right? It can be negatively charged, it can be neutral, right? As long as a nucleophile, right? So for this is acting as an electrophile, and this is acting as a nucleophile, obviously, right? So after this reaction, what you get is actually this species, right? In order to not confuse you, I just give you this nucleophile, NuH, right? This NuH can be OHO, which is your water. It can be your H2NH, which is the ammonia, right? All of them contain a H, right? So these are nucleophilic addition. Same thing, A plus B to get C. Next one is your substitution reaction. Substitution, the explanation is one group of atom is replaced by another to give two products. So if you want the A plus B thing again, same thing. If you have a AB plus a C, you will get AC plus B, right? You must fulfill this criteria. So just like the above.
Okay, isn't this reduction also? Because like you add hydrogen in this.
Reduction. Is it a reduction? Then it depends on what's the nucleophile, right? If let's say, for example, that's a good question, right? For example, if I have this species, and then I add a nucleophile which is OH, H2O, right? I'll have this species, correct? So this is carbon, so it's 0, 0, this is minus 2, so this is plus 2, right? For this is 0, 0, this is minus 1, this minus 1 is still plus 2, right? So in fact, for this kind of scenario, it depends on what is your nucleophile, right? If let's say your nucleophile is a carbon-based nucleophile, right? For example, R minus, right? For example, R minus, after I do the attack, I'll have R attached here. And then if you count again, originally is plus 2, here is 0, 0. Let's say this is carbon, so it's still 0. Here becomes plus 1. It becomes a reduction, right? So it all depends on what is the nucleophile. Since for this, it can be both The oxidation state can be both no change, reduce, or increase. We don't classify it as a oxidation or reduction, right? We classify it as a nucleophilic addition because this is not confirmed reduction, right? So this is a substitution. Same thing, you can have your electrophilic substitution. For this, you will encounter it in your arenes, right? Whereby you have a ring, and you can add species known as FeBr3. Let me write the equation first. Right. Right. Now the main species, you might think that how come I add these two and then in the end where's my Fe? Where's my iron? Alright. This is actually acting as a catalyst. Right? So it's regenerated, so there's no point writing in the product since it's regenerated, right? So the overall reaction is this plus a HBr. Alright, whereby your AB is this species, whereby your B is your hydrogen, C is your bromine 2, afterwards you have AC and then your B. This is known as an electrophilic substitution because the non-carbon based species, which is this Br2, is acting as a electrophile, right? Same thing, this benzene ring, like we've classified, is a nucleophile, right? So it all makes sense. This is electrophilic substitution. Next is nucleophilic substitution, right? For nucleophilic substitution, usually you have a polarized CX bond, right? You react with a nucleophile. Same thing, it can be negative charge, it can have a lone pair whatsoever, right? So for now, I'll just take the nucleophile as NuH again. So after the reaction, you will have C nucleophile plus a HX, right? Same thing, AB plus C, you'll get AC plus B. And this is acting as a nucleophile, this is acting as a electrophile, right? And of course, the last one which you already learned, which is your free radical substitution, right? Usually for free radical substitution, it's quite easy to spot because this is in fact the only reaction we have learned which deals with radicals, right? So I believe you know the example, which is just this plus Br2 or Cl2, you need UV to generate CH3Br plus a HBr. Same thing, AB plus C to get AC plus B, right? And this is very important, which is your UV, and it's also very easy to spot because this is in fact the only reaction that you have learned which involves UV, right? So that's for addition and substitution. Next, elimination. Opposite of addition involves removal of atoms or groups of atoms from adjacent atoms to form multiple bonds. So for this, same thing, we want the analogy, right? So for just now, remember addition we have, what's addition? A what? A plus B to get C, correct? So for this, it's just C becomes A plus B. It's just the reverse of addition, right? So for example, the example will be this just that is the reverse, right? You will eliminate or kick out these two adjacent species to form back the unsaturated bond. The next is a rearrangement reaction. It involves the migration of atom or groups from one site to another within the same molecule, right? For this is not as common, right? So for rearrangement, if you want an analogy, it will be just A to become A prime, right? Because it's just a simple rearrangement. Not necessarily the whole molecule rearranged. It might be just some parts of the molecule. So for example, I can have these species, right? X, and after the rearrangement, the X goes to here, right? This is a rearrangement reaction. The next is hydrolysis, using water to break bonds apart to end up with two or more products. So hydrolysis is quite obvious, right? Because like what the word hydrolyze suggests, you need water, right? So most of the time you have AB plus water to get AH plus BOH, right? Usually the water breaks apart, one joins here, one joins here. It can be the other way around also, the OH join here, the H join here, right? Depending on the exact reaction. So hydrolysis we have learned already in O levels, which is the hydrolysis of the ester, right? You have an ester group. If you hydrolyze it, of course with the help of acid, you will have your carboxylic acid plus your alcohol, right? Next is your condensation. The condensation is actually just the reverse of your hydrolysis, right? For this is just two molecules coming together to form a bigger molecule with the elimination of a small molecule such as H2O or HCl. So it's just the reverse of this, right? Whereby your AH plus BOH combine to form your AB plus H2O. It can be H2O or HCl or some small molecules, right? The key point is that it must be small, right? Need not be H2O, it can be HCl. So this is actually just your esterification, which is this reaction with the help of acid, right? This is actually your condensation. Your esterification is a condensation reaction. For this is the reverse of esterification, right? Reverse of esterification is known as hydrolysis, right? Next is oxidation. For this already taught you how to obtain the oxygen states. So if let's say you have a species like this, right, an alcohol, if you were to oxidize it, you will get an aldehyde, and if you were to oxidize it, you will get a carboxylic acid, right? And let's say we replace this with a H, right? So these can be further oxidized to give you this species, which can be further oxidized to give you your carbon dioxide, right? So these are different stages of oxidation. So now, why are these steps oxidation? Same thing, you can obtain the oxygen state of this carbon. So for this hydrogen, it is +1, this is -1, so this is 0. For this, same thing, -2. Make a mistake, sorry, yeah, correct. So this is -2, this is +1, so this is +1. So this is -2, this is -1, this is +1, so this is +2. Okay, and so on. So for this, it will be a +4. For this is also a +4, right? So in fact, from this all the way to here, you will see that it's actually a stepwise oxidation process, right? And if you were to use a reducing agent, what will happen is, although this is not possible, right, we are just discussing it on paper, so it's okay. So if you were to use a reducing agent on carbon dioxide, right, this is not actual reaction, you know, just use to illustrate, right? So if you were to use reducing reagent, you can go all the way back, right? Same thing, you can analyze it using the oxygen state method, and you realize that their oxygen states will decrease, right? It's just the reverse of this. And lastly is an acid-base reaction. It's just a transfer of H+, right? Acid-base is the easiest to identify, but a lot of people cannot identify. I also don't know why, right? Maybe because the structure is too complicated. You can have some fanciful structures, and they can have some fanciful functional group, and they say that, okay, this species is like that, and after some kind of reaction, I'll end up with this. and then they will ask to identify what type of reaction this is. It's actually just a very, very simple transfer of H plus, whereby this is transferred to somewhere else, right? So this is the easiest to identify. So for this acid base, you can just write, you can see acid base is actually just a base plus an acid, which is HA, right? So you have a HB plus a A minus, right? Generic one. So now can you try this example next? This is actually a prelim question. Also take note, sometimes questions can be a bit tricky, right? Because organic chemists do not know how to balance equations, right? But that's a fact, right? So what they tend to do is, not they don't know, they tend to be lazy. They write something like, okay, A plus a C, A plus a X2, okay, AX. This is obviously not balanced, right? Because the X, where it's gone to, and there should be a hydrogen somewhere here, and where it's gone to, right? But to chemists, they understand this reaction because the main part of the reaction is not about this, it's about this transforming to this. So they don't really care about balancing equation. But sometimes students see this, they'll think that, okay, it must be an addition. Because I have A, I have B, I get C. But they forget to analyze the other X, which is lost. Correct? And perhaps another H, which is lost. So in fact, this becomes a substitution instead of addition. So just be careful with that, right? Okay, good. It's a nucleophilic addition, right? It's a not. It's a nucleophilic addition because this R is adding to here, right? What about MgCl? Where did it go to? Is it lost? Why can't I say that it's a nucleophilic substitution since the MgCl is lost somewhere? This is not catalyst, right? Remember, it's not regenerated because it's added to the reagent already, right? Catalysts don't add to the reagent. Now if you look at these species, there's a negative charge here, correct? What do you think the MgCl will do? What's the net charge of MgCl? No, MgCl is plus 1, right? See, MgCl2 is neutral, right? So I remove one Cl, it becomes MgCl plus. So this plus is actually responsible for what we call it chelating, or you can say ionic bonding to this. Correct? So it's in fact added to it, it's not really substituted, it's not removed. Right? So it's an addition reaction, and this is acting as a nucleophile, right? Because we already identified this as a electrophilic species. So this is hydrolysis, very good, because water heat this out, although I never draw the other product, right? The other product is most probably ammonia or something. Right? What about this?
nucleophilic sub.
Yes, nucleophilic substitution. Right? Because this acting as a nucleophile, this is a iatrophile, and this is substituted somewhere, probably lost as water, right? Usually nitrogen will be lost most probably in the form of ammonia, while oxygen is in the form of water, right? So identify the nucleophilic and iatrophilic sites for each reaction. So for this case, this is as good as identifying the nucleophile and iatrophile, right? For this, the iatrophilic site is this carbon, right? For the nucleophilic site, it is the R, like what we mentioned, right? This is actually your polarized sigma bond nucleophile. You have a R, you have a Mg, you have a Cl. Doesn't matter why is this, right? Why you are interested in actually this bond. So we already established like just now, because this is similar to R lithium, right? So same thing, Mg is less electronegative than R. So you can think of this species as a R minus. So this is actually the nucleophile. For this, same thing, right? Identify the nucleophile and iatrophile. For this, the iatrophile is your carbon and the nucleophile is your oxygen, kicking the nitrogen out. And lastly, for this case, same thing. Your nucleophile is either of these nitrogen and the iatrophile is this carbon to kick this O out. Right? These are your nucleophilic and iatrophilic sites. Right? Next. So yeah, this one is 7, right? 8. So you should have a 9. Yeah, right? Organic reactions. Organic reactions involve the reaction between nucleophiles and iatrophiles involving the use of curly arrows, which shows the movement of electrons. The tail of the electron shows where the electron comes from, while the head shows where it goes to, right? We always say that it's an electron source to an electron sink. So before we go into detail about reaction mechanism, let's look at the two most common arrows, right? One is the homolytic fission. So for the forward reaction, I already written there, as well as the backward reaction, right? So for forward reaction, the bond breaks and the two bonding electrons are split equally between the two atoms, forming radicals. And the movement of electrons is shown by the half-headed arrow, right? Half-headed means the movement of one electron. So one electron goes to B, one electron goes to A. And the backward reaction, same thing. One electron comes forward, another electron comes forward to form the bond. So you usually occur between atoms with similar electronegativities. For example, peroxides, right? So for species containing the peroxide functional group, right, they will have this kind of structure. So for this bond, OO bond, you can form a radical, right? And after the homolytic fission, you have a RO radical and another RO radical, right? Now, why do they only occur between species with similar electronegativities?
Because it's in the middle. Because like
What cannot be between O and H?
Because then, since O is not like significantly more electronegative, then electrons will be more likely to go to oxygen instead of H.
Correct. Okay, this is like a type of war game. So while these two are pulling, I just cut the ribbon, correct? So electron will go one each. If let's say I have O and H, while they are pulling, I cut the ribbon. Both electrons will go to here because it has a greater pulling power, we call it, right? So this is why free radical substitution always occur between, for example, chlorine, bromine, etc., right? And next is heterolytic fission. Same thing, forward and backward reaction already illustrated for you. For the backward reaction is similar to just now that nucleophile attacking electrophile arrow, right? Think on a lot of students draw wrong, right? It is wrong to draw it like this. For example, I have A, B. Let's say B is the electrophile. It is wrong to draw like this. Okay, why? Yes, it must be from the electron or negative charge, because it shows the movement of the electron, not the atom. And it is wrong to draw it like this. Right? It's always from the electron source, which is here, to the sink. not the other way around. Okay, this is not telling you how the atoms come together. It's about the electron movement, right? So these are some things to take note. And next, for heterolytic fission, the bond breaks and the two bonding electrons are split unequally between the two atoms, so that one atom will keep both electrons forming an anion, and the other one forms a cation. Right? Charge is balanced. So if the positive charge lies on carbon, it's called a carbocation. If the negative charge lies on the carbon, it's called a carbanion. Right? As illustrated below. So can you give me some species which will undergo heterolytic fission like this and like this? So what must X be for this to occur?
Negative. So it can be like F, O, N.
F, okay, O,
Nitrogen.
N. Okay. What about this case? Hydrogen, okay. Well, it's quite rare for hydrogen. What else?
Lithium, sodium.
Okay, good. Lithium, right? Usually you have lithium. Sodium, not that much. Just now we have seen another one, which is our MgCl, right? So these species will can cause the formation of a carbanion, right? So the movement of electrons is shown by full-headed arrow, indicating a movement of a pair of electrons, and usually occur between two atoms with different electronegativities. So now describe the mechanism of heterolytic fission of CH3Br and CH3 lithium.
Probably more negative than carbon.
Yes. In fact, most of the hydrogens have electronegativity higher than carbon. Take note of your electron source. For this is from the bond, right? It's always from the bond to somewhere. Right. Next, this is a section which I not say invented, which I find is quite important. It's called pattern finding, right? In organic chemistry, a lot of students stumble at these kind of questions, and these kind of questions have become is quite popular nowadays, right? So these two questions are actually from prelim paper, so you can read yourself. After reading, you can try this.
Methanoic acid and methanol.
Yes. What? Ethanoic acid? You sure? Methanoic acid? You sure?
Methanoic acid and methanol.
Ethanoic acid got how many carbon?
2 carbon.
2 carbon, right? So how many carbon does this have?
Wait, no. Propanoic acid.
Propanoic acid,
Yeah,
okay.
you can't see.
Yes, right? A lot of people forget this C. So it's actually your propanoic acid and your methanol. You don't have to know what reaction this is. You can just deduce it, right? This is a breeding question. This is also a breeding question, right? It's a Claisen condensation. How do you deduce it?
Just replacing the alkyl groups with like the groups here.
Do you draw it out yet?
I just kind of wrote down, just did them.
Okay, I don't know the answer yet, but this should be quite easy to deduce, right? For those people who don't know, you can just split this, right, into this part and this part, right? So it's actually just using this to attack this, or if you don't think of the attack way, also can just this react this, and this OR is somehow picked up, right? So next, delocalization and resonance. This resonance part is only added to this year's syllabus, right? As stated here. So it's actually, I don't know if it's a good thing or a bad thing, right? Delocalization and resonance. Same for electronic effect, stereo effect, right? As well as mechanism of polar reactions. So I find that it's a good thing because it can help students to understand more. Nevertheless, they have removed quite a few things from your syllabus as well, so it's balanced. So by now you should be familiarized with drawing line bond structures. So now we look at why do we need to consider delocalization and resonance, right? So you should know how to draw carbonate anion by now, right? Which is like this, right? So you have learned that double bonds are stronger than single bonds, right? So it's very obvious that these bonds should be stronger than these two bonds. But in reality, scientists discovered that all three bonds are the same in strength and of equal in length. So what's happening? Right? Why is that means if you were to say it that way, that means this structure is wrong, correct? Because this clearly says that this one is stronger and this is shorter. So in fact, in order to counter such a problem, right, which we call it an inadequacy of bond line structure, we introduce a concept of resonance. So in resonance structures, a double-headed arrow is used to represent the individual structures, and the structures is drawn in square brackets. Right? So by drawing it this way, we can say that, okay, the double bond can be anywhere. Let me rephrase. If we draw it this way, we say that the double bond seems like, right, is moving between these 3 bonds, right? It can be on any one. But in reality, you will not have a scenario whereby, okay, 1 second is like this, the next second is like this, the next second is like this. It's rather a hybrid structure between these 3, right? In other words, a mixture of these 3. So you cannot really isolate this or this, right? It's actually a hybrid structure. And these kind of structures are known as resonance structures, and they show the charges in different places, indicating their delocalization. So this is actually a delocalization process, right? Delocalization is strongly related to resonance, so that's why I put them together, right? In fact, when you resonate, you will delocalize a negative charge, right? So they are very, very closely related. So a common misconception is that students tend to treat the resonance structures as different entities. However, resonance structures represent one entity, and it does not flip back and forth between the resonance structures. That's why this entity is sometimes known as the resonance hybrid. So it's really a hybrid between these 3. And an analogy of this is to think of a unicorn. People always think that unicorns are offsprings of horses and rhinos, but a unicorn has features of both, and it doesn't flip between these 2. And you cannot describe a unicorn just by using the features of a horse or rhino. You need both, right? Correct? So therefore, this is the energy for resonance. It should be noted that delocalization of charges allows the charge to be moved, to be more dispersed and stabilized. And this stabilization is more commonly known as resonance stabilization. So for example, if you only adopt this structure, you'll see that negative charge is on 2 atoms. If you draw it this way, this negative charge can be on all 3 atoms, right? So in fact, each atom will acquire 2/3 charge, right? So compared to a previous one whereby they hold 1 full charge, this is more stable because it's more dispersed. So we call this resonance stabilization, right? So aforementioned, the head of the curved arrow shows where the electrons go to, tail shows where it comes from. For the section on resonance and delocalization, you should take note that the arrows do not represent actual movement of electrons. They are just drawn to help chemists understand the delocalization, right? So I may draw arrows in this section, but that's only to illustrate how the electrons move, okay, in the resonance form. So it's not actually moving, because like what I mentioned, these 3, this exists as a hybrid structure, correct? By existing as a hybrid structure, there's no way for it to move because it's already there. I just draw the arrow to help you illustrate it better, right? So although it might seem difficult to draw those arrows for resonance, you just need a few basic rules, right? Right, you just have to follow some few basic rules of drawing resonance structures, right? This part will be a bit more technical, right? So just pay attention, but I will guide you through step by step. Some schools only teach very, very briefly, right? Which I find might as well don't teach, because you don't understand anything from the basic ones, right? So next, there are some rules to follow. These rules are very easy, I guarantee you. So the first rule is called avoid breaking a single bond, right? So although resonance structures involve rearranging electrons, all the atoms must still be connected in the same order, no matter what. Breaking a single bond would change this rule. Thus, single bonds cannot be broken, and the tail of the curved arrow can never be placed on single bonds. Why? Now, because if let's say I have this thing, and then I place the tail on a single bond and move it like this, what I will get is actually this species plus X minus, and I will break the single bond. So this rule is violated. So this is not correct. However, if let's say I have this species, right, and then I draw the arrow like this, it doesn't violate anything because no single bonds are broken. I'm only breaking a double bond, right? So this is acceptable, right? Later on we'll see some practices. So one example is this, right? For example, I have this system. It's wrong to draw it like this. No matter what is the product, you don't have to care, because as long as I break the single bond, I'm wrong, right? So resonance structures cannot break single bonds. Take note. That's the first rule. Next, rule 2, never exceed an octet for second row elements. Elements in period 2 can only contain up to 8 electrons. This one is already learned. Therefore, for period 2 elements, the number of bond pair and lone pairs can never exceed 4. One example is this, right? Is this difficult? Right? So for example, I have this species, right? If let's say I were to draw the arrow like this, it simply means that these 2 electrons come back down to form a bond here, right? And what I will get is this species, which is clearly a violation of my octet rule, because now carbon have more than 8 electrons, right? So this arrow is not allowed. Although this rule is quite dull already, right? But sometimes students can still get wrong, right? The rule is clear for the above example, but it may not be so straightforward if bond line structures are used. So care must be taken when dealing with bond line structures by counting the correct number of hydrogen atoms. So for example, now I have this scenario, right? Same thing, lone pair. And by the way, I can draw the lone pair coming back down. I can draw a negative charge coming back down. It means the same thing, exactly the same thing, right? So now I just draw it like this. A lot of people think that, okay, nothing is wrong, I'll get this. But they forget that there's actually 2 hydrogen here. So if I draw it this way, means that the 2 hydrogen is still here, correct? This is clearly a violation of my octet rule. So this is less obviously seen, right? So students, some students may not understand the... Are you okay with the arrow movements? If not, I can use this to demonstrate for you, right? So by now you should have already learned that there are some atoms which can contain more than 8 electrons. They are mostly atoms from period 3 and higher, most commonly sulfur, phosphorus, chlorine, etc. Therefore, for such atoms, they can have more than 8 electrons. This is just what you've learned in chem bonding, right? Hypervalency. So for example, this arrow movement, you have this lone pair coming from sulfur to the bond between C and S. So now you form a double bond, and this sulfur acquires a positive charge, right? Because you give away 2 electrons, right? So for now, okay, carbon doesn't exceed any electrons, right? It's just nice 8, but for sulfur you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it is possible because sulfur is from period 3 and below, right? So take note that the second rule is only violated if a period 2 element has more than 8 electrons. If it is perfectly alright if it has less than an octet of electrons, as the octet rule is not broken. If you break it, you must exceed, but for this, you never exceed. For example, this kind of movement, right? All of these are of course examples. Later on we'll see why the arrow is like that, okay, and perhaps not the other way around, which is like that, right? For now, they are just purely examples. So for this example, can you tell me whether any rules are broken? You can just write rule 1, rule 2, right? What is any rules broken? You may wish to draw the product, right? This might help you see things clearly. So for example, for this case, right? If I were to draw the arrow like that, it simply means that these 2 electron, which is from the pi bond, this is the sigma bond, from the pi bond shifts here, right? So after the shift, the sigma bond is still here. The other things, no change, but these 2 electrons move to here. So now the double bond is here. Right, this is what it actually means. It's actually quite straightforward. So you have this species, right? Obviously, you broke the octet rule, which is rule 2. So this arrow is not possible, right? So A, this arrow is wrong. For B, B is okay, right? Because it doesn't break rule 1, it doesn't break rule 2. So B is okay. So after the movement, what species do we have? After the arrow movement. You can think of it this way, right? You have this species with electron here. Originally O is like that already, correct? So if this moves to O, you have this species, correct? And does it have a net charge? This is another thing students always get confused with. They don't know whether there should be a negative charge or positive charge or whatsoever, right? So very simple, right? I've really included this formula, right? In order to calculate whether there's any charge, take the number of valence electrons minus number of lone pairs minus bracket number of bonding electrons divided by 2. So for example, this case, oxygen, number of valence electrons is 6 of course, because it's from group 6. Minus number of lone pairs. Is there any lone pairs? Yes. 1, 2, 3 lone pairs. Right. Sorry, not lone pairs, lone electrons. Take note. So 6 minus 6, and then minus a bracket number of bonding electrons divided by 2. This is the bonding electron. So minus 1. So the charge is minus 1. In other words, this oxygen will have a charge of minus 1. So I can draw it either this way or this way. Doesn't matter. Or sometimes people tend to draw it this way, right? Which I call it less correct because you are not illustrating the negative charge. So you don't even know whether your charge is balanced. So it's better to draw it this way, right? So this is the final species that you will get, of course, plus the other thing, right? This is wrong because you're breaking, because you are exceeding of that structure, right?
Did you just use lone pair of electrons to form a double bond with this C?
No, it's this pi bond, right? Shifts here. So after the shift, you have, remember, whatever they never touch, you leave where it is, correct? You never touch this lone pair. What you're doing is just shifting this pi bond to here. So you have this species. Same thing, divided is root 2, right? Good.
That's a valid.
You sure? Take note of this. Try expanding the structure by including all the hydrogen and see whether it violates any. Violates the octet rule, right?
That's breaking a single bond.
Correct.
That's break.
Correct. But you can always draw it my way. You have this, correct? So originally nitrogen already got lone pair. So now if I were to shift this pi bond to here, means these 2 electrons are transferred to nitrogen. It doesn't break a single bond, and does it exceed the octet rule? No. 1, 2, 3, 4, 5, 6, 7, it's still 8. So this is acceptable, right? This is correct? This is correct?
I think so.
Yeah, it's correct. Right, then this one? It's the same as this, isn't it?
Oh yes, hydrogen.
So you're actually exceeding out of that rule. See, it's not forming a double bond with H. There's a carbon there, remember? It's carbon, carbon, carbon. And this carbon already have 3 hydrogens. So is it possible for this lone pair to come back down to form a double bond here? No, because you have exceeded the octet rule for this carbon. Right? So next, seldom in resonance structures do we involve only one arrow. In fact, if you look at all these, there's only one arrow, right? Very simple. Whenever more than one curved arrow is used, all curved arrows must be taken into account in order to determine if any of the rules have been broken. For example, the following arrow violates the octet rule, which is this, right? Because it violates rule 2. But if I were to add in another arrow, it's actually correct, right? Why is this correct? Well, for this kind of reactions, for this kind of resonance structures with a lot of arrows, how do you analyze it, right? For beginners, in order to analyze such an arrow, what you do is that always start off from the end of the arrow, of the consecutive arrows. For example, the end, this is the end, I'll call it. Or do you prefer this to be end? This one is the end, so you always consider this first, right? So ignore all the other arrows except this. So now if I consider this arrow, for this you will need to draw what is the, I'll call it the product after this arrow movement, right? Take note, you have these two arrows. You have this arrow and this electron, either one moves here. Okay, you will have which species? Does it break any rule? If I were to expand the hydrogen, origin is like that, right? You don't break a single bond, and you didn't exceed an octet rule, because these two electrons, after you shift here, they become like that. On this carbon. These carbons still have 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Right? And take note, this carbon now acquires a positive charge. This acquires a negative charge. Same thing, you can use these to explain. Right? Take note, I just demonstrate this again. Originally is like that, double bond, correct? So after shifting, the hydrogen is still here. Right? In order to calculate the charge here, number of valence electrons for carbon is 4. Minus the number of lone electrons. For this, there's no lone electron, so it's minus 0. Number of bonding electrons divided by 2. So I have 1, 2, 3, 4, 5, 6. 6 bonding electrons divided by 2, which is 3. So 4 minus 3 gives me 1. So the net charge of this is plus 1. For this, same thing. And of course, charge must be balanced. Before that, net charge is 0. After that, net charge is 0. Right? So here is minus 1. Same thing, I can use that formula. 4 minus lone electron, which is 2. Minus number of bonding electron, which is 6 over 2, right, which will give me minus 1. So now I can get the charge of these two, right? So this is what I'll get after this arrow movement. Next, I consider the other arrow, right? The other arrow is from here to here. Same thing, if this arrow is from here to here, what it actually means is that these two electrons just purely shifts here and forms a bond. Right? So in other words, I'll have this species. This place I never touch, so I leave it where it is. I'm left with this species. Right? So same thing, when these two electrons goes to here, right, you actually, I'll call it neutralize this positive charge. Right? Same thing, I can calculate the charge as well. And I will get 0 for this and a plus 1 for this. Right? You may not get used to these kind of quick changes, right? But you need more practice, right? After much more practices, then you should be okay with it, right? For this charge, same thing, I can demonstrate to you this. Number of valence electrons for nitrogen is 5, minus lone electrons, which is none, minus number of bonding electrons, which is 1, 2, 3, 4, 5, 6, 7, 8, divided by 2. Right, which will give me plus 1. So this is plus, minus. Same thing, charge is always conserved, no matter which stage I am. So this is actually allowed. Right, and this is how you get this species, which is exactly this species. Right, more challenging. Right? So don't worry, just try this practice first.
This is a bit different from school one because school one they don't necessarily ask you to find out like the two different structures. They just ask you to draw the final entity product, the one with like this curve. What curve? Let me see. For example, something like this and the value.
Oh, this
Like they combine it together to form one diagram.
as in like that or
Let's see.
well, I'm teaching you the set, right? Mm-hmm.
Basically, they will have like this thing here.
Mm-hmm.
Maybe like two different structures, so then combine to form like this diagram. They ask you to draw this.
You mean ask you to draw this thing?
Yeah, to show.
But that one is not resonance. This is showing the final result of resonance. You are not drawing that resonance. This is how your resonance proceed, right? For example, you can take a look at prelim questions, right? This RG prelim question, right? How will you draw it? How will you do it?
As a resonance, if you don't see anything like this, the resonance part is very short.
Yeah, that's why most schools teach you very, very briefly, right? If you teach you very briefly, how are you going to do this question? It's a prelim question, right? You can take a look first. Same as this is about resonance structures. Suggest which resonance structure of diazomethane A or B is likely to be involved in the first step of the mechanism.
Is it related to finding like the flowers and actual flowers?
Where? Which one? This one?
Yeah, is it related to that?
Not really.
I think the more stable structure.
For this, you will need to learn about. You need to learn about resonance, which is this part. This is this part. Because after these basic rules, we'll be going through some basic drawing of resonance structures. Right. Because if you want, you can skip this. If you think it's a bit difficult, right?
Resonance is very short. It's only like 1.5 pages. Resonance is like 2 pages, so it's not a lot of stuff.
Yes, this one. Right. We involve this concept, which is, and then where's the other half? Oh yeah, here. Lone pair adjacent to positive charge. Right. So for example, just now that question. So for example, like this question. this structure, correct? They're asking why this is more stable. The simple reason is because this can be delocalized into this nitro NO2 group to form this. While for this and this you can't. So therefore 3 is the most stable because this negative charge is delocalized into the electronegative oxygen. Over this there's nothing electronegative for it to delocalize to. Right. So for now, if you are not very comfortable with the difficulty, we can skip this part first. Okay, we'll come back maybe in the later parts when you encounter problem as such. Alright? Can a flexible one, don't worry, right? So now we look at the electronic effect, right? This part is definitely applicable. Right, so for electronic effect, this is in fact specified in your new syllabus as well, right? So now electronic effects are due to the different substituent groups connected, which influences the structure of molecules, reactivity and rate of reactions, right? So as you go more into organic chem, you'll see how all these come into play. For here is more or less a brief intro, right? So what is the inductive effect? Inductive effect is the redistribution of electron density, blah blah blah, right? Via sigma bond. The most important keyword here is a sigma bond, right? Later on we'll see the conjugation effect, which is pi bond. Okay, so take note that this is not related to resonance, right? In fact, this is inductive effect since it's a sigma bond, right? Got nothing to do with resonance. Rule 1 is just now the never break a single bond, right? It's because of this rule, there's no relation. So inductive effect is heavily affected by the electronegativity of the atoms connected, where more electronegative atoms are electron withdrawing and pull the electrons closer to themselves, polarizing the sigma bond to a great extent, and making the adjacent atom having a greater partial positive charge. These are just these kind of arrows. I just use it to make students understand better, right? You shouldn't draw these kind of arrows in exams, right? So for example, if you compare fluorine, oxygen and nitrogen, fluorine you know that it's the most electronegative. So you pull the electrons to a greater extent than oxygen than nitrogen, which makes this having a greater partial positive charge. This one is slightly less, this one is the least. This is all relative, right? So if you only consider the inductive effect, you can say that the first molecule is the most reactive and will react with nucleophiles at the fastest rate. Because just now you have learned that nucleophiles are electron rich. They will attack a species, they will attack an atom whereby it's most positive, correct? So if let's say I have these 3 species present and then I throw in a nucleophile, which one do you think you will react with most? It will be this one, because it's the most positive one, right? It's just like magnet. So similarly, alkyl groups also have an inductive effect, and they are often known as electron donating groups. I believe you have heard about it before, right? Where they donate electron density to its adjacent atom, and the degree of donation increases with the number of alkyl groups connected. The reason behind this is known as hyperconjugation, which I will explain to you next time, right? In the following chapters, right? So for example, you have 1R group, 2R group, 3R group. You see that the electron donating effect is different. Take note that the CCl is just as polarized because you are not changing this atom and this atom, correct? It's still CCl, CCl, CCl. Just that for this, the partial positive charge is the greatest, second greatest, and this is the smallest because you have more electron donating groups. So same thing, if you throw in a nucleophile, you will react with this fastest, followed by this and this, right? Quite logical. And you should be able to deduce that distance also plays an important role in inductive effect. So if there's a same group connected but it's further away, then it exerts a weaker inductive effect, no matter whether it is this kind or this kind, right? So same thing, you have a nucleophile, throw in, you react with this the fastest because it's the closest, right? So next is the conjugation effect. Conjugation is the redistribution of electron density via pi bonds, and take note that this is heavily related to resonance, right? And conjugation effect is heavily affected by presence of lone pair or conjugated double bonds, and it can be predicted using resonance drawing in the previous section. So since we have covered the, just look at this, right? So for example, conjugation effect. For this, if you were to look at the double bond, right? Will the double bond be more electron rich or less electron rich than a typical double bond? Typical one, that means like this lah, right? Will it be more electron rich or less electron rich? The answer is more electron rich, right? You might think that this O is electron withdrawing one, correct? But since we have never thought about resonance, I cannot explain to you why it's electron rich, right? In fact, you will realize how important resonance is to understanding whether the ring will be electron rich, whether the double bond will be electron rich or poor in the chapter of A rings, right? For example, like this case, do you think the ring is electron rich or electron poor?
Electron rich because it's a delocalized electron.
Yes, because this electron can delocalize, correct? For this same thing, it can delocalize. This section is actually just this section, right? It's the same thing, right? Just that now it's an alkene. Same thing. What about this? Will it be electron? Will the ring be electron rich or electron poor?
Electron poor.
Electron poor. Why?
Because the pi bonds from is made with the delocalized electrons.
Yes. Okay. So this is actually electron poor. So if let's say I throw in a nucleophile, right? Sorry. If I throw in an electrophile, you will react at which position?
It's not any position.
No, it's not any position.
Oh, is it like this whole thing, not like just the ring?
Just the ring.
The double one.
You sure? Yeah. Which place? Here. There's so many places. Don't know, right? See, this is the strange thing about organic chemistry, right? Not strange. This is the, how do I say it? If let's say you have this species, which is this, right? If you throw in a nucleophile, for example, a nucleophile, where do you think this will add to? Some people think that okay, it might add to here, it might add to here, it might add to here, or maybe somewhere else, right? In fact, the most likely place is actually this place, and you will never add to this place, right? And in the chapter of Arians, you'll learn this reaction, whereby you have this is what we call phenol, right? If you were to react phenol with bromine 2, you will get a mixture of products, whereby the Br can be here, or here, right? Now the question is, why the Br cannot be here? Doesn't make sense, right? As of now, right? And sometimes, for this kind of species, if you add Br2, another strange thing occurs. Okay, you realize that the Br only adds to this position, and not this position.
This is something to do with the delocalized electron, how drawing effect.
No, it's about resonance, right? Explaining purely by saying that okay, there's electron withdrawing effect is not sufficient. It's just like, why is the apple red? Then you say that because it's a fruit and it's crunchy, therefore it's red. Okay, it's not related to that. For example, of course, I can have different groups connected here, right? Like this kind. And then I ask you, so for now, if I add bromine 2, will it be like this case or like this case?
To be the same.
This one.
Yeah.
Then if let's say, if it's like that,
Maybe if that's right.
first one, if it's like that,
Same
to the same thing. How do I predict? Now what if I add this to this? What will I get? See out. Will it be this case or this case?
Second one.
This one?
Yeah.
Why? The answer is the first one. Why? Mind blown. Okay. Never mind. Okay, if let's say you have time, you go and read the section on the previous part, right? You will solve all these mystery. You can predict all of these with ease, right? So it's okay. So if right, so if you only consider the conjugation effect from the examples, you can see that OH is actually an electron donating group for this, correct? By increasing the electron density of double bond through conjugation, while the CHO is acting as an electron withdrawing group by delocalizing, by decreasing their electron density. So considering only the conjugation effect, it can be said that molecules with electron donating groups make the double bond or benzene ring electron rich to react with electrophilic species faster and vice versa, right? So this is talking about only inductive, this is talking about only conjugation effect, right? So if we were to look at the overall effect, right, you'll see that OH is actually an electron withdrawing group by the inductive effect, and it is an electron donating group by the conjugation effect. So this is where it becomes confusing. So when does it act as an electron donating group, and when does it act as an electron withdrawing group? Correct? Now the key criteria is the question to ask yourself is whether there is a pi bond, right? So if there is a pi bond conjugated to it, it will act as an electron donating group. If there is no pi bond conjugated, it will act as an electron withdrawing group. So for example, in this case, right, versus this case, can you tell me if this group acts as an electron donating or withdrawing group? This is a donating or withdrawing group? So you get this? Withdrawing. Take note, this is not conjugated. Okay, this is conjugated, this is not. So this is a donating group, this is a withdrawing group, right? So it should be quite logical to think that for saturated molecules, inductive effect is the only determining factor because there's no double bond, right? And the inductive effect is only determining factor for the overall electronic effect, and is affected by first electronegativity, second number or the length of the alkyl groups, which is this, right? So for molecules with unsaturated bonds conjugated to the substituents, you have to also consider the conjugation effect on top of the inductive effect, right? And although I cannot tell you which effect is stronger, inductive or conjugation, but scientists have found this list, right? So this list is very, very trustworthy. So it tells you the net effect. This is for conjugated cases. So this is the most activating, or you can say the most electron donating. This is the most electron withdrawing, right? So this is just for a reference, and H is here, right? So you can see that OH is a electron donating group, whereby this, which is here, is a electron withdrawing group, right? It's already listed here. So now we should not memorize the trend, but reason out why it's like that. Okay, don't go memorize, oh, this is stronger and this is stronger, this blah blah blah. If I were to give you two, you should be able to rationalize why this has a weaker electron withdrawing effect than this. Okay, it's all about understanding the concept, not about memorizing. Memorizing no use one. And just throw you a new one and ask you to explain. If you don't know how to explain, then GG, right? So take note. And lastly is the stereo effect. This is a quite a simple effect, right? So stereo effect arises from the fact that each carbon occupies space and the approach of reagents could be hindered by bulky substituents, right? Such effect is known as a steric hindrance, and one example is the reaction below, right? This is a fast reaction, this is a slow reaction. And I've really drawn the space filling model for this and this. For this, the X is attacking this carbon. Same thing for this X is attacking this carbon, which is embedded inside. So obviously this is faster because this is sterically hindered, right? This is just your steric effect, and it's quite simple to understand, right? So it's the most activating, this activating. You see the next one. 12 acting is 14 I can skip as well, because this is related to resonance, right? You can go see and practice these yourself. So in fact, this is all for this part, right? So for now, you can work on some practices. Let me tell which practices. You can practice all except 3 and 4, right? What trend do you see? I'll walk you through. This part is quite obviously this part, correct? So after the reaction, if let's say both are pointing like that, you'll go in. If both are pointing like that, you'll be coming up towards you, right? You know how to read this going in and out, right?
Yeah.
Thing. This is for this part, and this double bond is gone, simply is replaced by a double bond in the middle. This one got not much diff. Next, for this reagent, if let's say both are facing the same side, which is the C's, very good. So afterwards, both will face the same side as well. Both will go in. If both face the opposite side, both will face the opposite side. Right? So this is a trend, right? So let's look at 3, right? Since 3 is easier to analyze. Is 3 correct or wrong?
There's like no stereo isolate.
Hmm?
There's no stereo.
You sure? But this one I already show you in 3D, right? Here just show you that one is up, one is down. I can redraw it in the side view such that I draw one pointing up, one pointing down. That is also possible. I don't have to die follow this, right? So for this, number 3, is it possible? So 3 resembles which one? This case, right? This one? Is this cis or trans? The double bond. In fact, whenever you sure? Or is there no cis or trans? There's no cis or trans, correct? So it doesn't really matter. Or you can think of it as it's trans to a hydrogen. So whenever you are confused, you can always simplify this into something you know, right? So for this, I'll simplify into this plus this x, right? So what will be the predicted product? In fact, if let's say I want to make my problem solving easier, I just simplify to this now, right? Because this is definitely this case, correct? And these two must always be connected. I'm not changing these two. So if I were to react this with this, what will I get? Remember, these two are still connected. I just draw it this way. Correct? So after the reaction, I have a new double bond here, which is here. Alright, so this will just form a bond with this, whereby X can either be up or down, doesn't matter. It can either be on this side or this side. It's the same thing. Up or down doesn't matter. Because it's trans, right? Trans doesn't mean this one must go down, this one must come up. But it can also be this one coming up, this one going down. Because it can be either way, right? So this is actually correct. Because this is exactly the product. Yeah.
Why is it from this shape?
You see, this part is this one. Correct. Just that now these two are connected. Right. For this reaction, there's no change to R group. I'm only changing this part to a single bond here. So originally this part is connected, so after the reaction, since there's no change to whatever happens here, it's still connected. Correct? So it's actually just taking this and like that. Right? So 3 is allowed. Right? In fact, if you cannot see, do you have a pencil? Right? This. Part, this is actually this part, and this part is just this part. Right? The other groups which is here is just used there to confuse you. But you just have to follow the trend, right? Nothing has happened to this double one, CO double one, it's just the CC. No, right? This is all about understanding this concept. So now let's look at 1, right? 1 seems quite straightforward as well. Same thing, this part shouldn't be a problem, right? So same as this. Let's look at it this way. Right? So we have this kind of connection here, right? So this resembles this part. Just that this is both page, so it doesn't really matter, right? So if I were to follow this trend, but now I have this combined with this is, you can call it a trans or C, it doesn't really matter, right? So after I connect these two, what will I get? Let's draw the dotted one first. How should this bond be? This bond should be coming out or going in. And it's this bond. After I form it, should it be coming out or going in? You sure? Going in, huh? So this must be like that, right? Then this point is like that, of course. This point is like that. Then what about this point? Coming out or going in? Or can it be both? Now I see, I just cover this part. Cover this part. Now you have two separate species, correct? This resembles this part. This is neither a cis or trans, so it's just like this. It can be either up or down, left or right. Correct? Now I simplify this problem further. You have this and this, right? Just treat it as an R group, right? And just rotate in your mind, right? Such that it becomes the same orientation as this. So now this one resembles which one? This one, the first case, correct? So for the first case, if this is pointing like that, after a reaction, it will point inside, correct? So if I point inside, that means this one should be like that. Sorry, inside. So after a reaction, I should get something like this. This one is a trans, or is like that, correct? You can either point in or out depending on how it's orientated, like what I told you just now. So this can either be like that or like that, doesn't matter, right? So now I just have to find out if the final product give me this geometry at this connection or this geometry can really, because either one is acceptable. Alright, so does it give either this or this? Not so straightforward. Because I swap the bond with hydrogen. This is about the next chapter called isomerism already, right? Whether you know how to interpret such structures or not. Of course, you know that I can either draw it this way. Let's say I have a junction here, R, another group H, and it cannot be H, sorry, R prime, and R, right? If I can either draw it this way or this way, or this one coming out or this one coming out, correct? Need not be this hydrogen one. So you know how to swap between these few structures, correct? So this same thing, I can have this coming out, this one going in. So this one is the same as hydrogen coming out, this is hydrogen going in. And then I can replace this with a normal typical kind of bond, because I don't have to know all three bonds to know the geometry one. I just have to know one bond. So it can either be this, or another case is both hydrogen coming out. So does it fulfill any one of these? Yes, it does, which is this one. So if 1 is correct, 3 is correct, 2 must be correct. Have you done such MCQs before? A is 1, 2, and 3. B is 1, 2. C is 2, 3. D is 1 only. Right. So since 1 and 2 are correct, so since 1 and 3 are correct, 2 must be correct. Right? 2 is just used to confuse you. Some people see 2, they don't do this question. Right? But actually you can just think of it this way, just by analyzing 1 and 3 first before analyze 2. Right? 2 is just used to waste your time. So there are some questions which are like that, right? You just take note. Now this one should be quite simple, right? You can refer to the front part. Why? Remember your ring is made of a ring of this, correct? So each of these is sp2.
Oh wait.
Right?
Oh yeah. Oh, what type of sp?
See? Here what?
Isn't that TSP3?
You sure? Remember you have something connected to sulfur, and sulfur is connected to 5 other things. Alright?
6, 10, 20. Oh. Okay, yeah.
So the answer is D. Another way to think about it is, instead of thinking of it in the which one is hybridized, which one is what hybridized state, right? Another way to think about it is to think of its shape, right? As long as its basic shape, I'm talking about its basic shape, is tetrahedral. If you didn't realize it, it will be sp3. This includes CH4, ammonia as well, and of course your water, because the basic shape is tetrahedral, right? Basic shape, that means you also count the lone pair. Now if the basic shape is trigonal bipyramidal, it will be DSP3, because there's 4 in total. 4 bond pair and lone pair. So it's 4. For these there's 5, and of course for 6, which is your octahedral, will be your D2sp3, right, and so on. And then if you're wondering, my school never teach DSP whatever, right? So now see this question. Put it somewhere else. It's okay. Right. I remember one year they got asked about the D2sp3 thing. Right, I'll find you next time. So the answer is D. Okay. So next time we try question 5, right? So which one is the sigma bond?
Either this one or this one.
So which one? This one. So is that a sigma bond formed by sp2 overlap?
No. This one. Okay, N is sp2, then C will be.
You sure this N is sp2? How do you learn? Remember the summary? For carbon, nitrogen, oxygen, right? You can use this. So if you say there's a sp2, there must be one pi bond connected to that N, correct? But there's no pi bond.
So it's sp.
It's a sp3 one. There's no pi bond. 0 pi bond is a sp3. Right? In fact, there's a lone pair there on nitrogen, which makes it sp3.
But then C will be sp. So be sp3.
Which one?
The C here will be sp3.
Yeah, it's sp3.
So this will be wrong.
Mm-hmm.
I think we're just not present.
Oh, not present.
Yeah.
Oh, okay, correct. I thought it's present, so D is correct. Okay, so it's not present. Next question. Right. Oh yeah, correct. This question, the hybridization one. Right, you already know the answer. which is DsP3, right? So you can't say that they cannot answer, right? So TJ 2011 prelim. For those people who don't understand why there's a need for hybridization, they will never be able to do this question, right? They'll be stunned because, got such thing as D, man? That's their first question, right? So now this should be easy. Let's skip to this. Around the aluminium only, not the others.
SB3.
Mm-hmm.
It should be 3 hybridized and 1 unhybridized.
You sure? SB3?
4 unhybridized.
4 hybridized, right?
Hybridized, yeah. Based on this shape.
Mm-hmm. And don't have to. Just draw the tetrahedral enough. Okay. Next.
That's fine.
You sure? That's how I calculate. Hydrogen, hydrogen, hydrogen. Aluminium, aluminium. Right. Which one is more electronegative? Carbon or aluminium?
Carbon.
Carbon. So, hydrogen is what?
Yes.
Remember the method that I told you? Plus, 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 minus, minus, minus. Right? Then for this case, how? Do I put a minus plus?
Here we are.
Or put another minus plus here? Which one is more electronegative? Carbon, right?
Carbon.
So carbon will have the minus charge. But is this correct? Is this structure correct? Carbon got how many electrons?
4.
Then this one?
It's 5.
Yeah.
It's a meditative one.
How to dative? See, carbon bonded to 3 hydrogen. So it's left with how many electrons?
2.
You sure? Carbon is from group 4. So you already used 3. So it's only left with 1 electron. Then how does it bond to aluminium? 2 aluminium. Here? Then this one how? Here? Then this one how? If you say it's dative, then how to dative? Like that? Because apparently if you want dative like that, you need 2 electrons, correct? Like that. Then how this aluminium bond to the others? Right, you should have this question in mind. Don't worry, a lot of students also stumble on this question, right? This is not exam one, right? It's your school's one. So what happened is that who says a bond can only be formed with 2 electrons? For this case, there's no choice but to deduce that, okay, there must be half an electron here. That means 0.5x. There must be half an electron here, 0.5x. Quite unbelievable, correct? But there's no other way to do this question other than assuming that it is a half bond. And it should be quite obvious because you already stated here, okay, in which 2 electrons are shared across each AlCal bridge. Correct? Which means that there's 1 electron here, 1 electron here, correct? Which further hints you that it's half an electron from X and half an electron from Y. 0.5, 0.5. Right? So now same thing, since here is 0.5x and you know that C is more electronegative than Al, instead of writing a full minus, it will be half a minus, which is a 0.5 minus. Here also have a 0.5 minus. So nothing else changed. The concept, the method is still the same. So in total, C is minus 4.
But there's such thing as like half an electron.
Yes, there is. This bond is known as a, what we call it in Chinese, 三锌二乙 bond. Right? In English, it's known as a 3C2E. 3C because there's 3 center, but there's only 2 electrons keeping this 3 center. That's why it's called 3 center 2E bond. Usually what we deal with is a 3 center 4E bond. For example, aluminium, chlorine, chlorine. You have seen this structure, correct? It doesn't violate any rule because precisely there's 4 electrons within this 3 center. So this is the normal kind, this is the abnormal kind, but it still exists, right? And of course there are other questions, other prelim questions that have 3C2E concept, right? So this is one of it. So part 3.
We don't have an electron, is it considered?
Not really half an electron, but there's only 1 electron here, 1 electron here. Half from this, half from this, right? So which bond is stronger, X or Y?
Y.
Y is shorter or stronger? Stronger.
Stronger.
Why? Because?
It's more S character.
Not more S character. Remember, this bond only got 1 electron maintaining it. What about this? There's 2. Correct? If you're still confused, see, this aluminium got 3 electrons. 1 electron will bond to the CH3, another electron will bond to the CH3. So it's left with 1 electron. Correct? That 1 electron, we think of it as split half-half. So half an electron will go here, half an electron will go here, which will bond with half of the electron from this C, half the electron from this C, and so on. Correct? So this bond is actually formed by 1 electron. This bond is actually formed by 2 electrons. So obviously this is stronger. Okay, that's the explanation. There's nothing to...
S character with the orbitals to
right?
explain strength.
If you use S character, then there's no way to explain this. How do you find a hybridization state of this? Correct? So it's not about hybridization state, it's about, very simply, the number of electrons that make up that bond. Right? So in fact, if you were to heat this compound, what you'll get is just AlCH3 3. It simply breaks like that, right in the center, to form this more stable species. Right? Because for this species, everything, all the bonds have 2 electrons. Right? So that's why these can act as a catalyst. Because we don't want catalyst to be not reactive one. Right? So this is very reactive for the reason of these 1 electron bonds. Right? Interesting, right? Couldn't expect them to ask these kind of questions, right?
Yeah.
Never learned before, right? But it's all making use of what you have learned, right? Including this and this. For this, maybe lah, but maybe a bit off syllabus, but
Give this line, I don't understand what it's supposed to mean.
Oh, yeah.
Usually there's information inside, but it doesn't mean much.
no. You're supposed to deduce that, right?
Yeah.
Okay, so the rest you can go back and